In 1931, Subrahmanyan Chandrasekhar calculated, using special relativity, that a non-rotating body of electron-degenerate matter above a certain limiting mass, now called the Chandrasekhar limit at 1.4 m, has no stable solutions. His arguments were opposed by many of his contemporaries like Eddington and Lev Landau, who argued that some yet unknown mechanism would stop the collapse. They were partly correct. A white dwarf slightly more massive than the Chandrasekhar limit will collapse into a neutron star, which is itself stable. But in 1939, Robert Oppenheimer and others predicted that neutron stars above another limit, the Tolman-Oppenheimer-Volkoff limit, would collapse further for the reasons presented by Chandrasekhar, and concluded that no law of physics was likely to intervene and stop at least some stars from collapsing to black holes. Their original calculations, based on the Pauli exclusion principle, gave it as 0.7 m. Subsequent consideration of neutron-neutron repulsion mediated by the strong force raised the estimate to approximately 1.5 m to 3.0 m. Observations of the neutron-star merger GW 170817, which is thought to have generated a black hole shortly afterward, have refined the TOV limit estimate to 2.17 m. Oppenheimer and his co-authors interpreted the singularity at the boundary of the Schwarzschild radius as indicating that this was the boundary of a bubble in which time stopped. This is a valid point of view for external observers, but not for infalling observers. Because of this property, the collapsed stars were called frozen stars, because an outside observer would see the surface of the star frozen in time at the instant when its collapse takes it to the Schwarzschild radius.